R2, which means a plane, is colored with two colors, and I'll explain what this means. You have to prove there exists monochromatic equilateral triangle with side length one or √3. All right. So monochromatic means all the vertices are same color, and equilateral triangle means equilateral triangle, and R2 is colored with two colors in the sense that every point is assigned a color. Let's say red and blue, for example. All right. And okay, so let's go with these two questions. Is there anybody who has seen both of these two questions?
Actually, I have an idea for two, and it is very similar to a question of problem-solving strategies. But I think this is not the exact question, so I'm thinking about it.
Right. So, what's your idea?
Like basically, we have to create that rhombus with 60, 120, 60, 120, and if one is not there, then something like √3 would be there, and we have to like construct the proof. But I know that like this should be our starting point, that rhombus thing.
You can try that and see if that works. Do try that, and if you get a solution, tell me, and then I'll share the link and you can show it to everyone. If it does work, if it does not, then go on trying. And so yeah, let's.
Also, sir, can we use some theorems or lemmas like which are well known but do not have a name in INMO? So, for example, we know that the reflection of the orthocenter lies on the circumcircle.
Right.
So can we use that directly because it does not have a name but it's well known? So can we use it directly?
As long as you know the proof and I know the theorem, you can use it. So yeah.
But how do I know that the person checking the paper knows the theorem? Like,
just solve the problem for now. Let's forget about those things for now. Okay. I mean, if you think it's not well known in the actual INMO paper, then what you can do is, if you think it's well known, you state it. If you don't, like, you should always know the proofs of the things that you're using, right? So if you are in a doubt that this may be considered to be not well known, then you should just state the theorem and write it as a lemma or something and prove it. Doesn't take much time, to be honest. And you have time in INMO. Like, you have 4.5 hours. Make use of the time. For now, let's try these two problems again. Maybe I'll do a Q&A session at the end of the class where you can ask like logistical questions like this. What should I do in INMO? So, okay, is there anybody other than... Oh, please go.
So, second question is done.
Second question done? Okay, what's the idea?
I create a hexagon with each side of length 1, and I may connect all of its, and I make all of its diagonals.
Okay, so what I'll do is, I'll give you the link of this. I'm not sure how to do that. Figure it out.
I think it's the padlock share thing.
Okay, so I think I have the link. I'll just give it in the chat here.
Sir, also please see that option change to anyone with the link. It is restricted. I cannot access it. So please change it to the option change to anyone with link.
Right, I'll do that. Yeah, I think you can access the whiteboard now.
No, sir.
I changed the settings. You should be able.
Please share it again.
Just try it once more. I think it should work.
Yeah, thank you, sir.
Cool.
Why is it not getting? Cannot. It's view only. It's view only, sir. Please give me edit access.
Right. Yeah, it's done.
So I'm in the second.
Yeah.
Okay.
All right. So what are the silents?
There you can see there are six equilateral triangles with side length 1 and one equilateral triangle with side length root 3.
Okay. So 1 second. So these are length 1. You're saying, right?
Yeah.
These sides are these are length 1.
This is length 1.
And this is length root 3. Why is this length root 3? 1 second. Let me check. Okay. Yeah. Yeah. That's true. Fine.
It's two heights.
Yeah.
So what happens is, if let's say the central point has color A.
Yeah.
Now, if any one of these two, any two adjacent vertices of the hexagon have the same color, then we are done, right?
Right.
So, in order not to be done, we need an alternating color pattern. A, B, B, A, like this one is maybe A.
Yeah, so this is A, then this is B, this is A, this is B, and so this is again B, and
yeah.
Cool.
Ryan.
Beautiful solution.
Yes.
Why can't be two adjacent B's?
Because then we could make an monochromatic equilateral triangle of side length 1.
No, if there are two B.
No, two B's.
If this is A, this is B, this is B. What's the problem?
Oh yeah, that. Okay.
So AA can't occur. We know that. We don't know anything more than that.
I have tried this. I think in a hexagon setting, there is a possible configuration where none of the condition is satisfied in a hexagon setting.
We need that. BB. Okay, let's say that one is. How should I explain this? That what is done in the top left corner, that is B, and let's say the right one is B. But let's say the bottom left one is A. Okay, then our condition won't be satisfied, right? And so we want to avoid. We want to avoid consecutive, and you want to avoid consecutive A's.
This doesn't have a equilateral triangle, monochromatic equilateral triangle. But yeah, I mean among the vertices and the center of the hexagon.
Okay, so what we need to prove is that in a cyclic string of A's and B's, where you can't have two consecutive A's, then I can choose like what do you call it? B's like not consecutive B's, like B's with one letter in between. So I can choose basically like a B and then a B and then B and then A and then you understand what I'm trying to say? Like a B is in something and then a B in something. Like basically we're doing something like
No, but this doesn't work, right? I mean, this is a counterexample.
what you have made right now.
Yeah, B, B, A here, and A in between, and
Oh yeah.
here B, here B. This doesn't have a monochromatic triangle of length root 3 or 1. So yeah, like go on trying. That's what I can say. Take some points and go on trying.
Sir, another key observation we can make is that suppose if two points of same color have distance 1, then that would mean that on that line, like points of 1 will be like consecutive. How should I say that? For example, like if we extend, let me draw. Like
if you have 2 points of distance 1, then what?
For example. For example, then suppose they have the same color A and A.
Yeah. Can you guys see what I'm drawing? I'm writing A and A. Can you see that? Are you guys seeing that? I'm writing on the second board. You guys are.
Yeah, sir, we can see that.
Yeah. Okay. Suppose they have A, then this has to be B, and this has to be B.
Basically, on this line, everything would go on to be A. Basically, with distance 1. Like, how should I say it? Like here, if we extend to distance 1, then this should also be A.
Why is that?
Why? I'll do like basically we have proved that only here logically. Should I prove that regressively? Because
so he's saying if we have 2 points of distance, distance 1, and they are of the same color, then everything along the line which are distance 1 away.
Yeah, not every point on the line, but the configuration shown that way.
So you are saying this B is not possible. Why isn't it possible? I agree with you. It's not possible. Why isn't it possible?
I'll show it on the I can show it on the third page.
Right.
Suppose 2 points have distance 1, and suppose on the contrary that here is a point with B on this line. This is B, suppose, and these two are A's. Then we draw a circle like this, and then draw these equilateral triangles to get that hexagon.
Okay.
So we get a contradiction. Let me show the. Then that would force this to be B. That would force this to be B. But now we have got a equilateral triangle. This is an equilateral triangle with a side length √3. So this leads to a contradiction.
Right. Very good. Now we know that this is A, this is A, this is A. If these two are A, it's obviously possible that this is A and this is B or something, right?
But we can get a AA thing because of that previous thing only. We can get it because we have shown it previously, and we can suppose on the contrary that we can draw a circle of radius 1, and if all points on that circle are B, then we would get a triangle of √3. So we can easily assume that there are 2 A's with distance 1.
I didn't follow you, but okay, I get it probably. Because so you're saying we had this circle and we had 6 points here, and 2 of these have to be same continuously, because if they are alternating, then obviously we have a.
If we see logically, then in that hexagon thing we have proven 2 lemmas basically logically.
Okay, fine. So just to explain it to everybody, if in this hexagon everything was alternating, so if this was A, B, and so on, A, B, then what was happening is this A was becoming a equilateral triangle of side length √3, right? So therefore we know it's not alternating. So somewhere 2 consecutive vertices have to be the same color. So suppose without loss of generality, suppose these 2 are A. Then what? Who was talking right now? What's your name? Okay, anyone. What X has proven is that everything is.
So my name is Arjun.
Okay, what Arjun has shown is that everything. Let's say these are the integers without loss of generality. Then all the integers have color A. And can we draw a contradiction out of that?
can you repeat what did he just prove?
Right, I'll create another board. Come to board 4. Firstly, he said that there are 2 points which are at a distance 1 and which are of the same color. So the proof of this is suppose not, then we had that regular hexagon thing, right? Suppose not, then everything at a distance 1 must be alternating. And I mean, we don't need to do a hexagon or anything for that. We can just take the circle of radius 1 centered at A, right? If everything on this was B, then obviously we have equilateral triangles of length √3 here. All right, like points which are 120 degree apart form a equilateral triangle of length √3, side length √3.
Sir, actually, I have another lemma that any points of with distance 2 must be of the same color.
Any point at distance 2 must be of the
Same color.
same color. Okay, prove it.
I am proving it on the 5th page. Suppose on the contrary that just a second. That we here is a B, like and here is a R.
Which page are you proving it on? I can't see you.
I'm 5.
Okay, yeah, cool.
Now suppose on the contrary that they are different. For some, they now consider their midpoint with W log. Let it be blue.
Right.
Then construct these equilateral triangles here. Everywhere construct like equilateral triangles. This is blue. This must be R. Otherwise, we will get a like that 1 triangle. But here we have a contradiction because this is a √3 triangle.
This is a √3 triangle, you mean?
Yeah.
Yeah, so did everybody get it? So this is not relying on any previous argument. I'll just repeat it for everyone. What he's saying is basically any 2 points which are distance 2 apart have to be of the same color. Right? This is what he said.
Yeah, sir. So I tried giving the thing that like you said you could take this like the lemma that he's proving and say like the integers have like a certain pattern to their coloring, like A, B, but you can't find like an equilateral triangle like in those integers. So it's getting nowhere because there's no equilateral triangle with lattice all 3 points lattice points. So I don't know.
Yeah. Obviously. Okay, fine. So what we proved here is any 2 points of distance 2 apart has to be of different colors, of same color. Sorry, because if they are of different colors, then without loss of generality, let the midpoint be of the one of the colors. So let's say this is blue, this is blue, this is red. Then the point here, which forms an equilateral triangle of side length 1 with the blues and blues, this has to be red, because if it's blue, then we have already done. And this also has to be red. And now you can check that this has side length √3/2. So this whole side length is √3. This red to red, and this is √3, and this is √3. All right. So then we are done. Otherwise, we have found that any 2 points which are distance 2 apart have the same color. Now take any point, construct a circle of radius 2 around it. So if this is A, then everything on this is A. All right. And then from here, take another circle of radius 2. Then this is also, everything on this is also A. I don't know if this will work, but I'm just telling you, okay, this will probably not work, but yeah. Okay, forget about this. What can we get from there here?
I got another conjecture that the distance between any 2 points with like a length for let E be or suppose let L be any number less than 4.
Okay.
Then any 2 points of distance L must be of the same color. In fact, let's take L equal to √3 and we would be done.
Okay, let's see. How do you?
I'm on the 8th page actually.
I'm sorry, what was the conjecture again?
Distance. Yeah.
So, guys, where we are now is we have proved that any 2 points which are at a distance 2 apart, they have to be of the same color, right? So, if we can find 2 points which are distance 2 apart and different colors, then we have our contradiction. Okay, so try to do that.
We are almost done. Like, I've written a lemma.
If 2 points have distance 1, then they have the same color. Is that your lemma?
And we would, yeah. Now,
Okay, how do you
suppose
do that?
on the contrary that this is R, this is B.
Okay.
Take their midpoint and draw their perpendicular bisector. Choose a point here so that this distance is 2. I'll prove the existence of such a point. Actually, existence of such a point is trivial because this is 1/2, and take this like choose this x appropriately so that x square plus 1/2 whole square become 2 square.
Yeah,
so that's not
fine,
a problem.
That's fine. As long as 2 is greater than
Now-
half, it's fine.
Now this point can be nothing. Like this cannot take any color. Like if we see from here, then this should be R. If we see this argument, then should be R this 2. But if we see this argument, then that would force it to be B. So we have a contradiction.
What do you mean by this argument, that argument? I don't get your contradiction.
Like these 2 points have distance 1. These 2 points have distance 1. Distance 2. Sorry, I'm sorry. Distance 2.
All right.
And we previously proved the distance of any 2 point with distance 2 must be of the same color.
Okay.
So this must be R. But again, if we see the similar thing from this point, then this must be B.
Yeah.
So we are done.
Okay. So let's do the whole proof together now. So firstly, we proved that any 2 points which are at distance 2 apart have the same color, because if they had different colors, this is B, this is A, then this is B without loss of generality, and then there are these 2 points, these have to be A, and so we have found a equilateral triangle of length √3. So any 2 points which are distance 2 apart have to be of the same color. So take 2 points which are distance take 2 points which are distance 1 apart from each other and distance 2 apart from some other point. Then what we have is these 2 have to have the same color, because this and this has the same color, and this has the same color. So what I'm saying is A and B have the same color, and B and C have the same color, so A and C have the same color. This is what his argument was.
Okay.
That equality is transitive. But anyways, so yeah, this was an easy question. I think everybody has got it. Let's do question one now then. So
Sir,
two is
can
done.
you give another question so that I can try it for some time? Like.
Yeah. Okay. So let's think of some question. 1 second. Let me think of a nice question. Okay, let's do one polynomial question only, okay?
So I think I've got some progress on the first one, maybe.
Yeah, just 1 second. You can continue writing whatever you want to say in board number 11. I'll just write down one question.
Let me first check if my answer is right.
Okay. So Find all f. Find all polynomials f over the reals which satisfies this relation. So this third question and the first question actually have a
Sir,
similar idea.
I've already done this question too.
Okay, cool. So, okay, then forget about this question.
So my answer is wrong. Sorry.
Okay, so let f be a polynomial. F is f. Let's say f belongs to R of x, and f maps the integers to the integers. All right. Then this is a very general lemma. Yeah, you guys should know it. If you don't, then we are proving it right now, because you should remember this, because this is very helpful sometimes. That the f of the integers is integers, then prove there exists c1, c2, and so on in the integers, cn, such that f is cn x choose n plus cn minus 1 x choose n minus 1 plus up and so on up to c naught x choose naught. All right. So you can see this is a if and only if. The other direction is trivial, right? So if this is the polynomial, then on the integers, the binomial coefficients give integers, and their sum obviously gives integers. So if the polynomial maps integers to integers, it is indeed true that we have this nice characterization that it is a sum of binomial coefficients. Yeah.
So we need to prove that any general polynomial that p of x square. Wait, actually, I'll check myself. Sorry.
So we have a polynomial which maps the integers to the integers, which means that if you input an integer, f of 0, f of 1, and so on, these are integers. Okay. So if this is true, then f is the sum of binomial coefficients. And it's very routine. The problem is not that difficult, but it's very useful. So that's why I'm telling you. It just induct. This is not difficult.
I was asking about the first question. Like,
oh, sorry. Please go on.
Sorry. I was asking what the question was, but then I forgot I had access to the Jamboard.
Right. Okay. Cool. So I'll give you some hints for question number 1 for people who have been trying till now.
So the degree is same, right? But it's like the sorry.
For question 1?
No. Sorry, the degrees are not. For question 1, the divisor has degree to the n, like to n, And the other guy has a 3.
So firstly, x squared plus x plus 1 divides x cubed minus 1, as somebody pointed out as soon as I wrote the question. So you can see that x to the power px equals x to the some power n, let's say, is a solution to this, right? And any constant multiple of that is a solution. So p equals x to the power of n times c is a solution. And I'll tell you this: these are in fact the only solutions. So you have to prove that these are the only solutions. So I'll give you a hint. The basic strategy to do this is okay. So we can see that 0 is the only root, and we have to prove that 0 is the only root. So what we have to do is suppose lambda not equal 0 is a root, and obviously, okay. So firstly, the polynomials need not have roots and real numbers. It can be complex. So lambda not equal 0 belongs to the complex numbers is a root. So we have to derive a contradiction out of this, that if lambda is a root, lambda other than 0 can't be a root. And the general strategy to do this is to sort of construct an infinite family of roots, okay, and then say that okay, this is impossible because the polynomial has finitely many roots.
Every root of the p of x squared plus x plus 1 is a root of p of x cubed minus 1. Right?
Yeah, that's true. So from this and the fact that lambda not equal 0 is a root, you have to construct an infinite family. So basically what you have to do is, if you have to show that if some lambda is a root, that implies something else is a root, and from there you can find another root and so on. And you have to have some property which is, let's say, monovariant, so that of these roots, when you go from lambda to that other root, because then that property keeps on increasing, and so this cannot cycle back to lambda. And so in fact you do find an infinite family of roots, and that will be the required contradiction.
So okay. Root of what? P of x or p of x squared plus x plus 1, like?
No, p of x. You have a root of p of x.
Okay.
You want to find another root of p of x, and then derive a contradiction out of it. Okay, so in fact, I'll tell you what exactly you have to do in this case. Okay, in this case, take any lambda which is not equal to 0. Then mod lambda is something greater than 0. So this is the same as saying take some lambda such that mod lambda is greater than 0 and p lambda equals 0, right? And then you have to show that you can find some lambda dashed which has modulus greater than lambda, such that p of lambda dashed equals 0. And if you can show this, then you have the required contradiction, right? Because then for lambda dashed, you can find another number which has modulus greater than lambda dashed, and so on. And then you have an infinite set of roots, which is impossible.
So, but if lambda is equal to root of iota, then what will be the modulus of lambda?
What do you mean root of iota?
Root of iota is modulus 1, right?
Yeah, it's modulus 1.
Like iota is in itself a respect part again.
What is iota? Iota is e to the power of I pi over 2, right? The root of that is e to the power I pi over 4. So that has modulus 1. I mean, if you think of it in the complex plane, this is iota. So the root of iota will be on the unit circle halfway from iota. So this is the root of iota. That has modulus 1. But anyways, so let's go to a new board and let me further tell you what I want to do. So I want to say that suppose for contradiction, that lambda greater than 0 exists such that p of lambda equals 0. We want to find a lambda dashed with modulus greater than lambda such that p of lambda dashed equals 0. And here we have to use our previous fact that p of x squared plus x plus 1 actually divides P of x cubed minus 1. Okay, so how do we do that? So let's say x squared plus x plus 1 is lambda, okay? That would imply
X
that-
is complex.
that P of x cubed minus 1 is 0.
So
Right? Sorry?
X is complex, right?
Yeah.
Because real X might not exist.
Yeah. So x belongs to the complex numbers. In fact, this will have two solutions,
Yeah.
and let x be any one of those, and then P of x cubed minus 1 is 0, right? So if we can prove that x cubed minus 1, the modulus of this is greater than modulus of lambda, at least for one x, right? We have two such x. If for any one of these x's this is true, then we are done. Okay?
So modulus of x cubed minus 1 equals modulus of x minus 1 times modulus of x squared plus x plus 1.
Right. So modulus of x cubed minus 1 equals modulus of x squared plus x plus 1, which is modulus of lambda, times the modulus of x minus 1. Right? So if we can show modulus of x minus 1 is strictly greater than 1 for some x, so there are for x equals x1 or x2, where x1 and x2 are the roots of this equation, right? Then we are done.
So we should use the quadratic formula on x plus x plus 1 equal lambda, maybe. Like x equals, so
yeah, you can do that, but that will be a bit tedious. Let's try to find a nice way to show this. Okay, from this, now that you have this, this is not at all difficult to do. You can just bash this out even with quadratic formula or something else. Okay.
That is not tedious, sir. Sir, the roots of the equation are not tedious. They are simply cube root of lambda into omega and cube root of lambda into omega square.
Sorry?
Sir, the roots of the equation x square plus x plus 1, it is simply cube root of lambda into omega and cube root of lambda into omega square.
No, that's not true.
Why?
Why is that true? The roots are of the equation x squared plus x plus 1 equals lambda.
Yeah.
So why does that imply that cube root of whatever you're saying? You're saying that x equals omega times cube root of lambda, or what?
Yeah.
This doesn't satisfy this.
Okay.
I mean, why would there be any reason for this to satisfy this? Let's take the case lambda equals 0, okay? Then this is 0, but 0 is not a root of this. Okay, so what we have is right now x1 minus 1 is less than equal to 1 and x2 minus 1 is less than equal to 1, right? Because if one of them was greater than 1, then we would be done. What can we do from here? We know x1 plus x2 is what?
So I think I bashed it out. I mean.
Okay, very good. Like, you have solved the question. I mean, but I'll not bash it.
Okay.
It's fine to bash it out. Once you have this in an exam setting, I would advise you to bash it out. Don't look.
It's not enough actually, the bashing. I mean, it's.
I know it's short. I mean, once you have this idea, it's not that difficult to bash it out. And I would suggest that in fact you do bash it out in an actual exam. But now it's not an exam, so we are trying to find a nice way to do this. Let's do it in the nice way. Okay?
Yeah.
Okay. So what is x1 plus x2? 1, right? Or minus 1. x1 plus x2 is minus 1. All right. So we know that x1 minus 1 plus x2 minus 1. This is modulus what?
This is mod 3.
The modulus of this is 3, right? Then by triangle inequality, one of this has modulus greater than equal to 3 by 2.
Yep.
Or you can just say